Hello everyone, welcome back to my video of part 4 torsion. In this video, I will discuss a step-by-step analysis of structure under torsion. So I will show two examples of problem and how to solve it. So we start with example 3. So let me read the question first. A solid shaft ABC of 50 mm diameter is driven at A by a motor that transmits 50 kW to the shaft at 10 Hz. The gears at B and C drive machinery required power equal to 35 kW and 15 kW respectively. Compute the maximum shear stress in the shaft and the angle of twist phi AC between the motor A and the gear C, and then use the modulus of rigidity G equal to 80 gigapascal. So from the question, we know that the power from the motor is to transmit to the shaft. In this case, the power from motor is the input power, and the power at gears B and C are the output. The power, we can convert the power into torque. When we draw the free body diagram, the direction of the input torque will be opposite to the output torque. Alright, so first let we convert the motor power, the power of the motor P to the torque T, so that we can after that we can draw the free body diagram. So we have the equation of the power P equal to 2 pi f t. So we are going to convert the power from the motor, so I put here PM and also TM. Okay, so M is stand for motor. Okay, so from this equation we can calculate the torque Tm, so which is equal to Pm over 2 pi f, and we substitute the value. Pm is 50 exponent 3 divided by 2 pi f is 10. So from here we can get the torque from the motor, which is equal to 795.8 Newton meter. Okay, so similarly for gear B, so TB is equal to PB over 2 pi f. Okay, so that is the torque acting at gear B. So PB is equal to 35 exponent 3 and then divided by 2 pi f. So because the shaft is rotated at the constant frequency, so the frequency is constant, which is equal to 10, and from here the TB is equal to 557 Newton meter. And for gear C, okay, for gear C, so we can calculate the torque acting at gear C, which is equal to power of gear C divided by 2 pi f. So if we substitute the value, we get 15 exponent 3, okay, divided by 2 pi times 10. So here we get 238.73 Newton meter. Okay, so we get all the values for torque acting at the motor, and then torque for gear B and also torque for gear C. Now we will proceed by drawing the free body diagram of the shaft. Okay, now let me draw the shaft ABC. So shaft ABC. Okay, so this is the point A, this is the point B, and here is the point C. Okay, so I assume the direction of the torque for motor is directed to the left. which is here. So that is the torque from the motor, torque from the motor. Okay, and then so that the TB, the torque at the B and also torque at the C will be directed to the right, because TB and TC are the output torque. Okay, so from here Tm, Tmoto is equal to 795.8, and then the torque at gear B is 557, and the torque at gear C is equal to 238.73. So this is all the value that we calculated previously. Alright, now we have to determine what is the maximum torque. Okay, what is the maximum torque in the shaft? So first we have to analyze the shaft AB. Okay, so that so how to determine the shaft in section AB? So we have to do the imaginary cut, and then we draw the free body diagram for section AB. So we have here is 795.8, so that is for section free body diagram for section AB. Alright, and then we have the internal torque for section AB, which is equal to TAB. So from here for now we write TAB. Okay, and then we can apply the summation of force in x direction, which is if the force is directed to the right, we assume as a positive. Okay, so from the free body diagram of section AB, we can write that the TAB minus 795.8 is equal to 0. So TAB is equal to 795.8 Newton meter. Okay, so now we proceed with section BC. So what we have to do is we have to do the imaginary cut at section BC, and then we draw the free body diagram for section BC. Okay, so I rewrite again. So here is 795.8. okay, and then we have the torque at B. Okay, at point B is 557, and here will be the TBC. Okay, so applying the summation of force at x direction. Okay, the summation of force must be equal to 0 for static equilibrium. So from here we can write the equation for TBC is equal to 795.8 minus 557. So TBC is equal to 238.73 Newton meter. Okay, so now we have the torque, internal torque at section AB, and also internal torque at section, sorry, this is BC. Okay, so the question asks to calculate, the question is what is the maximum shear stress. Okay, so for this case, since the TAB has maximum torque, so the maximum shearing stress will be at the shaft at section AB. Okay, so we can calculate the tau maximum, which is equal to T C over J, and for this case is TAB, because TAB is the highest torque in the shaft. Okay, so C also TCAB and JAB. Okay, so first let's calculate what is the JAB. Alright, Okay, so JAB. So we calculate JAB. Okay, polar moment of AB. Okay, AB is equal to pi over 2 times C power of 4, which is equal to pi over 2 and C equal to 0.025 power of 4. So JAB is equal to 6.136 times 10 to the power of minus 7 m power of 4. Okay, so now we can straight away calculate the tau maximum, which is equal to T again, TAB times CAB over JAB. So TAB is TAB equal to 795.8. Okay, and then multiply by CC equal to 0.025, and then divided by 6.136 times 10 minus 7. So from here we get the value, the tau maximum equal to 32.4 megapascal. Okay, so we done for question A. Now question B is, what is the angle of twist for section for point A. Okay, point C. Okay, point C. Okay, what is the angle of twist for shaft AC? AC. So the angle of twist of shaft AC is equal to angle of twist of shaft AB plus angle of twist for section BC. Okay, so we can write the equation for angle of twist, which is equal to TL over JG, okay, for AB, and then plus TL over JG for section BC. Okay, so we substitute all the values. Okay, so T for TAB equal to 795.8. Alright, and then multiply by L. So the length AB equal to 1 divided by JJ equal to 6.136 exponent minus 7. And then multiply by G. G is equal to 80. Okay, 80 exponent 9. Okay, gigapascal. And then plus for section BC. Okay, so the torque is 238.73, and then time L is 1.2, and then divided by 6.136 exponent minus 7, and then multiply by G equal to 80 exponent 9. Okay, so using calculator we get the angle of twist for shaft AC equal to 0.022 radians, or in degree is 1.26 degree. Alright, so we done question 3. So now let's move on to we done on example 3. So now let's move on to example 4. Alright, example 4. The horizontal shaft AD is attached to a fixed base at D and is subjected to the torque shown. 44 mm diameter hole has been drilled into portion CD. So shaft at portion CD is the hollow. Okay. Knowing that the entire shaft is made from steel, for which the modulus of rigidity G equal to 77 gigapascal, determine the angle of twist at end A. Okay, so now the question is, what is the angle of twist at point A? Okay, at point A. So the angle of twist at point A basically equal to angle of twist for portion AB plus angle of twist for portion BC plus angle of twist for portion CD. Okay, so that is the total, that is the angle of twist at section at point A. So for this problem, let's start with the free body diagram. So we draw the free body diagram of the shaft. Okay, so the shaft consists of point D, point C, point B, and also point A. And then don't forget, portion CD is hollow. Okay, so and then we draw all the torque that acting on the shaft. So at point B, okay, so we have TB, okay, which is equal to 2000 Newton meter, and then we also have a torque at point A, okay, which is equal to 250. How do I know the direction of torque at B and A? So I applying the right hand rule. Okay, so based on that, I know that the direction will be to the left. And here we will have at point D, we will have the reaction torque TD. Okay, so from the free body diagram, we can determine what is the TD. Okay, so what we have to do is we apply the summation of force for x direction, okay, must be equal to 0. So from here, TD minus 2000 minus 250 equal to 0. So TD basically equal to 2250 Newton meter. Okay, so that is the value of TD, and the direction is towards to the right. Okay, so we highlight TD here. Okay. Okay, now let's draw the free body diagram for section AB, BC, and CD. So that after that we can later we can calculate the angle of twist. Okay, so I draw the free body diagram. So this is a free body diagram for section. So I start with section DC, okay, or CD. Okay, section CD. So I will have 2250 here, and also here will be the TCD. Okay, so TCD is hollow. So based on the equation of equilibrium, so I know that the TCD is equal to 2250 Newton meter. Okay, and then for section BC, okay, so for section BC, okay, so I draw the free body diagram. Okay, here will be hollow, and I have a torque 2250 here, and then I have here is the BC. Okay, so from here, from the free body diagram, I know that TBC is equal to 2250 Newton meter. Okay, how do I get the value of TBC? So by applying the equation of equilibrium. Okay, so now I proceed with the free body diagram for section AB. Okay, for section AB. Okay, so I take the part from right side. Okay, I take the part from the right side. So I will have here TA, which is equal to 250, and here is the TAB. Okay, so from the free body diagram, I know that TAB is equal to 250 Newton meter. Okay. Alright, since the angle of twist, the equation for angle of twist equal to TL over JG. So from here, in order to calculate the angle of twist, we need the value of J. So I recommend we calculate the J, the polar moment of inertia for each section before we can calculate the angle of twist. Okay. So now let's calculate the polar moment of inertia J for section CD. Okay, for section CD, so which is equal to pi over 2 times 0.03 power of 4 minus 0.022 power of 4. Okay, so here is equal to 9.044 times 10 minus 7. So the unit is m power 4. Okay, and then for section BC, okay, is equal to pi over 2 times 0.03 power 4, so equal to 1.272 times 10 minus 6 m power 4. And the last section is section AB. Okay, so the polar moment of inertia equal to pi over 2 multiplied by 0.015 power of 4, and this is equal to 7.952 times 10 minus 8 m power of 4. Okay, so we have the value of T. Okay, we have the value of J. Now we can calculate the polar moment, the angle of twist at point A. Alright, so the angle of twist for point A is equal to the angle of twist. So angle of twist for shaft CD plus angle of twist for shaft BC plus angle of twist for shaft section AB. So this is also equal to TL over JG, okay, for CD plus TL over JG for BC plus TL over JG for AB. Okay, so we substitute all the values. So TCD equal to 2250 and then multiply by 0.6 divided by 9.044 times 10 power of minus 7. Okay, and then multiply by 77 exponent 9. Okay, so that is for portion CD. And then for section BC, okay, the top is 2250. Okay, and then the length is 0.2 divided by J equal to 1.272 times 10 minus 6, and then divided by 77 exponent 9. That's all for BC, and then plus the top for AB is 2250, and then multiply by 0.4 divided by 7.952 times 10 minus 8 and multiply by 77 exponent 9. Okay, so using the calculator, okay, so we get 0.0403 radians. Okay, or we can convert into degree. The angle of twist at point A equal to 2.31 degree. So how to convert? So radians to degree. Okay, so you have to multiply by 180 and then divided by pi. Okay, that's all. We finished for example 3 and 4. this is the end of video part 4. Till we'll meet again in the next video. Thank you. Bye bye.